My name is Jerry Markov, and I'm from MSc Actuarial Science, presenting on the topic Markov chain modeling of HIV, tuberculosis, and hepatitis B transmission in Ghana. The work was authored by Dr. Clement Chumisi, Professor Louis Asiri, and Professor Isaac. The journal was in the interdisciplinary perspectives on infectious diseases, and the publisher was the Indawi Publishing Corporation. The problem statements. The problem is that traditional models struggle to estimate key metrics like infection and recovery probabilities. And then the objective of this study is to use a discrete Markov chain model to improve the understanding and prediction of HIV, TB, and HB transmission dynamics. So as mentioned, the model is the discrete time Markov chain model. The data was the secondary data from cohort studies on HIV, TB, and HB in a Ghanaian hospital. The techniques that we identified are transition matrices for discrete disease states, the maximum likelihood estimations, and decomposition using the eigenvalues and vectors. The key findings that were noted in the paper. Hepatitis B is more infectious over time than TB and HIV, and the first infection probabilities are low. And also, HIV-infected individuals have lower life expectancies than TB and HB. The conclusion was that Markov chain model effectively estimates and predicts disease dynamics. Confidence in the research or the findings. The study used a first-order time Markov chain model, and the study effectively addressed the objective by modeling disease progression through discrete states. The maximum likelihood estimation method was used for estimating the transition probabilities, and then we'll look at it in the next slide. So looking at the Markov chain model, it is used to model disease progression through discrete states, and it's given as the probability of xn equal to I, and giving xn minus 1 equal to in minus 1, or equal to probability of xn equal to I, and giving xn minus 1 equal to in. In this case, xn represents the health state of the individual, and then it denotes the state at time n, assuming the probability of transitioning to the next state depends only on the current state. So that's one assumption of the Markov chain model. It states that the transitioning to another state depends only on the current state. Now we continue to look at the transition matrix where we have a matrix P to be P00, P01, P02, and then these are divided into three states. We use the SIR model. The SIR model is a compartmental model used in epidemiology, and then it actually divides the population into three compartments. We have the susceptible, we have the infected, and then we have the removed. The susceptible state is actually the state where the person is not infected with the disease, but is at risk of contracting that disease. And then because we have the matrix in rows and columns, the first row, which is P00, and column 1, which is P00, tells us that the individual stays in the susceptible state. When we move to P01, that means the individual is moving from the susceptible state to the infected state. And then when we move from here to here, the individual moves from the susceptible state to the removed state. And then the removed state is actually the state where the individual either recovers from the disease or dies. The data was followed up for one whole year. And then the estimation, the transition probability matrices were estimated using the maximum likelihood estimated as mentioned earlier on. And then the maximum likelihood estimation is a statistical method used to model parameters of a model. In this context, the Markov chain model, we estimate for the transition probability matrices. And then the likelihood function follows a binomial distribution and is given as this. And in this case, to actually estimate the transition probability matrices, we need the formula Pij equal to Xij all over the Ni. But before that, given this likelihood function, we have Pij to be the probability of success, and that is transitioning from state I to J. And then we have Nx, which are the parameters of the model. We have Ni, which is the total number of transitions from state I. And then we have Xij. We have Xij, which is the observed number of transitions from state I to J. And so we would want to maximize this likelihood function to be able to get this. And how do we maximize this? Maximizing the likelihood function directly would be complex. So in that case, we maximize the log likelihood of this. And taking logarithm of this actually is a monotonic function, which tells us that it preserves the minima and then the maxima, and then it simplifies the differentiation process. What do I mean? When I take logarithm of this, and we assume that the binomial coefficient of this function is a constant, so when we take the derivative of it, we assume it's zero. Whether we keep it or we omit it, we still have this. So we ignore. When we take logarithm of this, bij 1 minus bij raised to the power nij, properties of logarithm, this becomes xij, logarithm of what? Bij plus logarithm of plus ni minus xij, logarithm of 1 minus bij. Now after taking the log, we try to differentiate it. We are still maximizing the likelihood function. So when we take log of that, and when we differentiate that, of course when we have log of bij, we are differentiating with respect to bij. So when we differentiate log of bij, we'll have 1 over bij, and then already xij is there, so it becomes xij over bij plus this becomes a composite function. So we also differentiate log of 1 minus bij. We actually get 1 over the 1 minus bij. But we also differentiate the negative bij again, and we get negative 1. So our positive changes to a negative, and then it becomes xij all over the bij minus ni minus the xij all over 1 minus the bij. Then we set our differential to equal to 0. When we set it equal to 0, this 1 ni minus xij all over 1 minus bij causes the equal to sign to be positive. And then we cross multiply, we group like terms, and then we make bij the subject. And then we get that bij is equal to xij, not forgetting that it's the observed number of transitions from state I to j, and then ni is the total number of transitions from state I. Now, looking at the matrices we have here, don't forget we are still using the SIR model. So we are still using the susceptible state, the infected and the removed state. So looking at the first one having a probability of 0.93, it tells us that 93% of individuals remaining in the susceptible states have 93% of staying there. And then a 6% chance of actually, when you are infected, you remain infected with a percentage of 6%. And then when you are in the removed state, you stay there with a percentage of 1%. And it goes on. But if you observe, even from our previous slides, we had the last state to be 001. That is because one of the assumptions of the Markov chain model is that when you enter, it's an absorbing state. So when you enter the removed state, you don't go back or you don't leave the process. That is why this is the removed state. So moving from the removed state to the susceptible state, that is, you have recovered from the disease. You cannot be at risk again. So we assume it's 0. And then moving from the susceptible state to the infected state is a 0. By you moving from the removed to the removed is 1. That is how come the last states of the matrix are all 0, 0, 1, and that is an absorbing state. Alright, so also we mentioned 3 techniques. We looked at the Markov chain, we've looked at the maximum likelihood estimation, and then we are coming to look at the composition using of the eigenvalues and vectors. So the eigenvalues and vectors approach actually is here to help us form transition probability matrices for n step over multiple time steps. So you realize that in the research paper, you realize that this was equation 14, and then it gave us equation 16, equation 17, equation 18, and this was done using equation 14. And then equation 14, we have Pn equal to Q, lambda raised to the power n, and Q inverse. And then in this case, Q is actually a matrix of eigenvectors, and then lambda is a diagonal matrix of eigenvalues. And then we actually, the procedure here is that we compute our eigenvalues, that's lambda 1, lambda 2, and then we find the corresponding eigenvector and form Q. And then when we do that, we find for lambda, then raise it to the power n. And then when we now multiply, we form our transition probability matrix, and then it goes. So it gives us this equation 14 that gives us this. And now we come to the generalizability. The study is context specific to the regional hospital in Ghana. but methodologies can be adapted for similar epidemiological studies in other regions. Some of the implications are insights into the spread and control of HIV, TB, and hepatitis B. It's useful for policymakers to design targeted health interventions. Early diagnosis and prompt treatment, especially for TB, are crucial for improving recovery rates. And looking at the improvements, we can extend the study to include one more diverse population across different regions. We can incorporate more comprehensive and data, including socioeconomic factors. We can consider longer follow-up periods to capture long-term trends. We can use more advanced models to capture the dynamics of the disease, co-infection, and other complications. We looked at the key findings, and I'll read it again. Hepatitis B showed a higher effectivity over time compared to TB and HIV. And then HIV-infected individuals have lower life expectancies compared to the other diseases. And then the methodology utilized the discrete time Markov chain model with data from cohort studies in Ghana. And the implication again highlighted the need for targeted public health interventions, especially for hepatitis B and HIV. Healthcare. So we recommend that this will improve access to treatment, this will strengthen healthcare infrastructure, and then the research, we can conduct longer term cohort studies, and we can integrate advanced predictive models. Thank you.